In this video, I want to discuss an additional theorem that's useful to prove triangles congruent. All right, let me give you an example where the theorems that we know so far will not work. All right, imagine that we had two right triangles, and we knew that the hypotenuses were congruent, and we knew that a pair of corresponding legs were also congruent. All right, is that enough to establish that the triangles are congruent? All right, think about what we can use. Does SSS work? No. Does SAS work? No. How about ASA? Nope. Okay, and there's no such thing as SSA, so I hope you didn't suggest that. So can you see that we're out of luck for this example? Okay, the good news is that this is a special case where SSA does apply. Okay, think back to the counter examples, if you know of some, of why SSA, why you can have two triangles that satisfy the requirements of SSA and the two triangles still not be congruent. Okay, it had to do with the fact that one of them could be an obtuse triangle and the other one could be an acute triangle. Okay, so obtuse angles is what got us into trouble there. All right. However, notice that in a right triangle you can't have obtuse angles, can you? Because the measures of all the angles have to add up to 180. So you already have a right angle, so you can't have another angle greater than 90 degrees. Okay. So that is a little hint of why, in this case, a form of SSA works. Okay. Now, because this involves the hypotenuses and a leg, we don't call it a special case of SSA, although you could, but that's just a longer name. We call it the hypotenuse leg theorem, or the HL theorem. Okay, so the HL theorem, that might help you to prove two triangles are congruent when the other theorems won't work. Okay, now you could establish other theorems for right triangles. Like, what if you had that the hypotenuses and an angle were congruent? Angle pairs. Okay, what about if you knew that the two pairs of legs were congruent, or a pair of legs and another pair of angles besides the right angle? Okay, in all of these three cases, it'll turn out that they'll reduce to one of the original forms. Okay, for example, for the HA situation, we have two pairs of angles that are congruent. Okay, let's discuss that one. So the A is more than the right angle. It says there's another pair of angles that are congruent. Okay, so let's say we had the hypotenuse is congruent again, and now we have another pair of angles congruent. Do you remember the fact that the angles of every triangle add up to 180? So you remember that if you have two pairs of angles congruent, then you also have to have three pairs of angles. Okay? So therefore, what does that mean? That means that when the HA situation arises, you could just as easily use ASA. Okay? So let's do the LL. For the LL, we have, let's see, that we have two pairs of sides and we have the right angle in between them. Okay, so can you see that that's a special case, or that is a case of SAS, right? And then for the bottom case, we have two pairs of angles congruent. We have the right angle plus this additional angle referred to as A, the A pair. Okay, so once again, that'll be another case of ASA. Okay, so the HL theorem is a really crucial one here. The other one's not so much. All right, let me close this video now by applying the HL theorem to a puzzle, a proof. All right, so think about this. You can pause the video and try to solve this if you like. Prove that if a point is equidistant from the sides of an angle, then it is on the angle bisector of that angle. All right, so try to solve that if you like. I will discuss with a diagram right now. Okay. So we have an angle, and we have a point that is the same distance from both sides. So let's be clear what we mean when we say that a point is the same distance from... Let's be clear what we mean when we say that a point has a certain distance from a line or a line segment. What that means is if you draw a stick that forms right angles, okay, you're making a statement about the length of that stick, that perpendicular stick. Okay, so the assumed situation is that this will, let's make our point maybe purple. Okay, we have a purple point, and we know that those two red sticks are congruent. That's all we know. Okay, is that purple point on the angle bisector? Okay, well, let's play with this now. So let's draw a line from the vertex of the angle to that purple point. Okay, so would you agree that that green line segment is the hypotenuse of two triangles that I just created? Okay, now would you also agree that for those two triangles, we know that they have the same hypotenuse because, well, they're sharing the same hypotenuse. We also know that we have a pair of legs congruent. That was the assumption. Okay, so can you see that the HL theorem applies? Okay, so therefore the two triangles are congruent. That's a fact. Okay, now hold on. If two triangles are congruent, doesn't that mean that kyptic applies? All right, let me remind you what kyptic means. Congruent parts of congruent triangles are congruent. Okay, these two right triangles, and they are right triangles, they're congruent. So all the corresponding parts are also congruent. Therefore, I can assume that these angles right here at the vertex are congruent. Well, that's the definition of an angle bisector, is it chops an angle in half. So therefore, if the conditions of this proof are true, then the point is indeed on the angle bisector of that angle.